Okay, so this is a review of the fast Fourier transform. So let's start from basics. So what the fast Fourier transform does is it maps an n-dimensional vector a0 through an minus 1 to another n-dimensional vector alpha naught through alpha n minus 1. Now, a really nice way to interpret this transformation is that the ai's are the coefficients of a polynomial. So you're given some polynomial a of x equal to a0 plus a1 x plus a n minus 1 x to the n minus 1. And the alpha i's are the evaluation of this polynomial a at n points. So alpha naught is the evaluation of a at 1. Alpha 1 is the evaluation of a at the point omega, which is a primitive nth root of unity, and so on. So alpha j is a evaluated at omega to the j, all the way to alpha n minus 1 is a evaluated at omega to the n minus 1. Okay, so these omegas are primitive nth roots of unity. They are solutions to the equation x to the n equal to 1. And over the complex numbers, this has exactly n solutions 1 omega omega squared through omega to the n minus 1. So this linear transformation, which is this discrete Fourier transform, is given like this. The jth row of it is 1 omega to the j, omega to the 2j, and so on. So if you look at the jkth entry, it's omega to the j times k. Right? So that's the jkth entry. And so the first row is 1, 1, 1, so on. The second row is 1 omega omega squared up to omega to the n minus 1. And the last row is 1 omega to the n minus 1, dot, dot, dot. Okay, so we'll denote this matrix by m sub n, or to emphasize the fact that we have chosen omega to be the primitive nth root of unity, we'll call it omega sub omega n, m sub n of omega. Okay, so now let's go back and to understand the discrete Fourier transform matrix, we have to understand the properties of the nth roots of unity. So let's go back and look at those properties. So remember, the complex numbers are best visualized on the complex plane. So there's the real axis and the imaginary axis. And in fact, the roots of unity will lie on the unit circle. So we draw a circle of radius 1, and there's 1, there's minus 1. Now, we are actually going to be assuming that n is always a power of 2. But for all these properties of omega, these are going to hold very generally. We might need the fact that n is even for one of these properties. Okay, but now where do the nth roots of unity lie? So omega, which is a nth root of the primitive nth root of unity, this angle would be 2 pi over n. So let's call this theta. Right? So that's the primitive nth root of unity, and then the nth roots of unity are just powers of omega. And remember, when you multiply two complex numbers, you add the angles. So omega squared, the angle doubles, and you'd be at 2 theta. So you'd be omega squared would be here at 2 theta, omega cubed, say omega to the 4th, 5th, 6th, 7th, 8th, 9th, 10, 11, 12, 13, 14, 15, 16. So that's the case where n equal to 16. Okay, so now there are a few properties that that omega is satisfied. So first of all, the nth roots of unity are just omega to the 0, which is 1, omega to the 1, omega to the 2, through omega to the n minus 1. Omega, again, is cosine theta plus I sine theta, where theta is 2 pi over n. Omega to the j is just cosine j theta plus I sine j theta. Okay, now here's another property, and for this property we do need that omega is, sorry, n is even. So if n is even, then omega squared is a primitive n over 2th root of unity, right? Because the primitive n over 2th root of unity, you would have theta prime equal to 2 pi divided by n over 2, which is just 2 times 2 pi over n. Okay, so that's one important property. Another important property of the roots of unity is that if you take, so suppose I take omega to the j, and now I look at all multiples of it. So I look at omega to the 2j, omega to the 3j, omega to the n minus 1 times j. Okay, so I look at a sum of n of these. So for instance, if I had j equal to 1, I could look at 1 plus omega squared plus omega cubed, and so on. So these are numbers that are equally spaced around the circle. So when I add them up, I should get 0. But actually, this is true not only for omega, but if I start with omega squared or omega cubed and I look at its multiples, then I'm just going to keep going around the circle in an evenly spaced way. And what I'll get is, this is going to be equal to 0 if j is not equal to 0. So if it's between 1 and n minus 1. But what happens if j equal to 0? Well, then this is 1 plus 1 plus 1 plus 1, so it'll be n if j equal to 0. Okay, so how would you actually prove this? Well, this is a geometric series, so you can use the formula for the sum of the geometric series, and you'll easily see that the answer is 0 in this case, and you can of course trivially see that it's n in this case. Now there's a third property of omega that we'll actually be relying on. So if we let omega equal to a plus b times I, then we can look at its complex conjugate. The complex conjugate of a complex number is just you take the negative of the imaginary part, a minus bi. So if omega is here, and it's a plus bi, where's omega bar? Well, it's right here. So omega bar is just going to be equal to omega to the n minus 1. Of course, what this means is that if you look at omega times omega bar, you get omega times omega to the n minus 1, which is omega to the n, which is 1. So actually what we have is omega bar is the same thing as 1 over omega, or omega inverse. Okay, so these are the properties of omega that we'll actually be using. And so now let's go back and look at this discrete Fourier transform matrix, or the FFT matrix. So it's m sub n of omega. So now one question we could ask is, suppose that we wanted to compute the inverse. So suppose I gave you the values of the polynomial at 1, omega, omega squared, and so on up to omega to the n minus 1. So I gave you this right-hand side. Can you now figure out this left-hand side? Well, the answer is clear. Well, in order to do that, what we want to know is what's m sub n of omega inverse, the inverse of this matrix. it turns out that this inverse has a very nice form. It's just the same thing as 1 over n times m sub n of omega bar. Right? Remember we said omega bar is the same thing as omega inverse, so it's just, it just happens to be this matrix. So let's see how would we show this? So what we would do is we'd multiply these matrices together. So we'd take m sub n over here. So we take m sub n of omega, and we take m sub n of omega bar, and we'd multiply them out. And of course, we want times 1 over n because that's what we are claiming. It's 1 over n times m sub n of omega bar. And now let's figure out, if we take the jth row of this, and if we take the kth column of this, and we just multiply the jth row by the kth column, then what we should get is the jkth entry. Right? So that would be the jkth entry of the product. So let's evaluate that. What would that be? Well, the jth row is just 1 omega to the j, omega to the 2j, and so on. And the kth column would be 1 omega bar to the k, omega bar to the 2k, and so on. So when we multiply these two out, what would we get? We'd get 1 plus omega to the j from here, and omega bar to the k. Remember, omega bar is the same as omega to the minus 1. So omega bar to the k is omega to the minus k. So we get omega to the j minus k. Now the next entry, so let me write this out. This is 1 omega to the j, omega to the 2j, dot, dot, dot. This is 1 omega to the minus k, omega to the minus 2k, dot, dot, dot. So the next thing we'll get is omega to the 2j times omega to the minus 2k. So you get omega to the 2 times j minus k, all the way up to omega to the n minus 1 times j minus k. And now remember what this, so if we call j minus k L, so this is of the form, if we let j minus k equal to L, then this is of the form 1 plus omega to the L plus omega to the 2L plus omega to the n minus 1 times L. And remember, a property that we saw is that this is equal to 0 if L is not equal to 0, and it's n if L equal to 0. What does this mean? Well, what it means is that this entry is going to be 0 if j is not equal to k, and if j equal to k, it's going to be n divided by n. So meaning that this matrix is 1 on the diagonal and zeros everywhere else. So it's the identity. Okay, so what this tells us is that the discrete Fourier transform and its inverse look very similar to each other.